Okay, this is paper paper 2, AQA A-level chemistry, June 2017. Right. So first one, we've got a scheme of reactions there, and we've got this halo alkane here in the middle. Okay, and reaction, draw the display of J. Well, J, you're reacting with sodium hydroxide in aqueous solution, so you get a nucleophilic substitution reaction. So we just draw out the halo alkane first of all. So we've got there. It says displayed, so you've got to draw every bond. You can't draw CH3, CH2. They usually ask that once per question somewhere, once per paper. Right. And the OH minus is going to come along, nucleophilic substitution, and that is going to go there. You get nucleophilic substitution when it's in aqueous solution. We see later, I think, in this one here, reaction 3, they've got the NaOH in ethanol, and you get elimination. Okay, so that's the answer to that bit. Right. Name the mechanism for reaction 2, and given essential conditions is that you only get the primary amine produced. Well, once again, it's going to be nucleophilic substitution. I'll just write that there. So here's your ammonia. So there's bromine there. And ammonia is going to, the lone pair is going to attack that carbon there. And the bromine is going to fall off. Now, it says here, what condition must you use to ensure that you only get the primary amine? Well, you've got to use excess ammonia. And the reason why you've got to use excess ammonia, it doesn't ask you why, but just to explain, is that if you make this product, you make the primary amine, well, that is actually a pretty good nucleophile as well. And so unless you've got loads of ammonia, this is going to react with the haloalkane, and that will give you a secondary amine. And the secondary amine produced, that will also a pretty good nucleophile. So that means that it can react again. You can have the tertiary amine and even the quaternary ammonium salt. So that is why you've got to use excess ammonia. Right. Okay, we've got a bit of a yield calculation here now. So, right. So calculate the mass in grams of the propylamine made from 2.52 grams of bromobutane. Let's work out the MRs of both of those first. So the MR of the bromobutane, which is C3H7B, so bromopropane, sorry, is, so that's 122.9. And the MR of the amine, so that's going to be C3H9N. The MR of that is 59. Okay, so, and we can see, let's think about how these react. Now, 1 mole of the haloalkane is going to give us 1 mole of that. It's a 1-to-1 ratio, the moles. So let's work out how many moles of the bromopropane we've got. Well, we've got 25.2 grams divided by its MR, 122.9. That gives us 0.205 moles of the bromopropane. So therefore, we're going to get we get 0.205 moles of the amine if we get 100% yield. So the mass of the amine for 100% yield is equal to moles multiplied by the MR of the amine, 59, which is equal to 12.1 grams. But the question says, assuming a 75% yield. So if 75% yield, then if it's a 75% yield, then the mass you're going to get is going to be equal to 12.1 multiplied by 75 over 100, which is equal to 9.07 grams. Give it to appropriate number of significant figures. Well, we should give it to 3 because all the data is given to 3 significant figures. So 9.07 grams is the answer there. Okay, now when reaction 2 is carried out under different conditions, so they mean here not an excess of ammonia, but presumably an excess of haloalkane, you get a compound with the molecular formula C9H21N. Okay, so what's going on there is we have replaced all, well, we've got a propyl group, 3 propyl groups, one there, attached to the nitrogen, the tertiary amine. It does ask for a skeletal formula, so we should draw it like this. Just check the right numbers of carbons, 1, 2, 3, that's right, and the same on this side, and the same down there. That is the skeletal formula of our product. Identify the functional group in the compound. Well, it's an amine once again. But its classification, we classify that as a tertiary amine. Okay. Right. Identify the conditions, and just tidy this up a bit. Identify the conditions and the reagents used in reaction 3. Okay, so if we look at reaction 3, well, that was when we got the haloalkane. So you've got C3H7Br. In reaction 3, it goes to C3H6. Okay, and it also told us, I think, didn't it? It said the oh, it doesn't give us the conditions, but it's actually sodium hydroxide in oh, so we want sodium hydroxide, but not in aqueous solution, in ethanol. If you have it in aqueous solution, you just get nucleophilic substitution. We want it to get elimination. How can we tell it's elimination? Look, if you go from there to there, you've actually eliminated an HBr molecule, haven't you? And from H7 to H6, and you lost the bromine as well. Name and outline a mechanism. Well, it's called elimination. And let us draw the mechanism now, okay? So I'm going to draw the the bromopropane. Now in elimination, remember what's going to happen. We are going to remove a bromine, and we're going to form a double bond between those 2 carbons. So that means we've got to remove a hydrogen from this carbon here, from the carbon next door. So let's go that one, okay? Right. So the hydroxide ion acts as a base. It accepts a proton, not as a nucleophile, so it's not going to attack there. It's going to accept that H plus there. That means the electrons in this bond have got to go somewhere else. And they go to form the pi bond between the 2 carbons there. It means this carbon here with the dot on it, that's got too many bonds. So we've got to lose the bromine, comes up as Br minus. Okay, we draw the final product. We've got propene. I won't put all the hydrogens on. We're going to have a water molecule. And there's the H, which has come from the haloalkane, and also we're going to get Br minus coming off there. Okay, on to some rate equation stuff now. Right. Rate of reaction. Right. The rate equation, question 2, between compounds A and B is given as that. So it's second order with respect to A, first order with respect to B. Figure 2 shows how the concentration of A changes with time. So you can see the concentration of A is dropping down here as with time, as it's getting used up. And what is the tangent of this? Sorry, what does the gradient of this line give us? Well, the rate of reaction in this case is actually equal to the minus of the gradient, the negative gradient. Okay, and it's going to ask us to draw a tangent at times 0. The initial rate is going to try and make us find out here. So if I draw a line, and if you look in the mark scheme, they're pretty generous about where exactly you draw that. They're not too strict, as long as it's reasonably in the right place. So there's my tangent. So get a mark for that. And use this tangent to deduce the initial rate. We've got to find the gradient of that tangent. Okay, so I'll draw some construction lines. So I've got that. I'm going to use this red triangle to work it out. Okay, so the gradient is equal to the gradient m is the change in y over the change in x. The change in y is 5 up here. So sorry, it's 0 down there, minus 5.5 up here. And the change in x is going to be, that's 11 minus 0. You work that out, it gives you 0.054 minus 0.0454. So the rate of reaction is going to be, it's minus the gradient, so we get that minus and minus goes, so we get 0.0454 moles per decimeter cubed per second. Right, now I think in the next part of the question we need to remember that the initial concentration of A in this experiment is 0.05. I think we need to remember that. So I'll move on to the next question now. Right. Okay, here we go. 2.3. The experiment was repeated with the same temperature and the same concentration of B, but with a different initial concentration of A. So in the first experiment, the initial concentration of A was equal to 0.5. We know the initial rate is 1.7 times greater than the original one, so we've got to find out the new concentration of A. Let's call that A1, and we'll call this one A2. And we don't know that, we've got to try and find that out. Okay, so the way I would do it is this. Well, we know the rate expression. The rate, it tells us, is equal to that, A squared times B. Okay, so let's do it for rate 2, first of all. So rate 2, this is the new one. That's going to be equal to K. The concentration of A2, the new concentration of A squared, multiplied by the concentration of B. And we know that rate 1 is equal to the concentration of A, the first one, squared, multiplied by the concentration of B. And we also know here, they tell us that rate 2 over rate 1 is equal to 1.7. So what we're going to do is going to sub these two values of that for rate 2 into this equation and for rate 1. So let's do that. So we get 1.7 is equal to K. Now, what is A2? We don't know. B. And then substitute in for value of rate 1. So we get the rate constant. Now A1 was 0.05, tells us there. So that's going to be 0.5 squared multiplied by the concentration of B. We can cancel a lot of this stuff out. So we get rid of the rate equations, get rid of the B's. And so we know there that 1.7 is equal to A2 squared over 0.5 squared. Let's rearrange that. A2 squared is equal to 1.7 times 0.5 squared. Do that in a calculator, you get 0.425. So take the square root of that to get A, we get square root of 0.425 is 0.652, and the units, of course, are moles per decimeter cubed. Right, it's a bit of a long-winded way of doing it, but I think you can do it sort of more on less mathematically than that, just more of a gut reaction. But I think that's the safest way of doing that particular question. Okay, so I'll just make some space here. More rate equation stuff in 3. Okay, question 3. Right, now this is a straightforward plug-in numbers into equations type question. So look, it tells us the rate equation here. It gives us the initial rate. It gives us the concentration of C and the concentration of D, and we've got to find out the value of the rate constant K. So let's rearrange that equation. So we're going to get K is equal to rate over C times D. Right, it's going to ask us for the units as well. So let's, before we do anything, let's work out the units. So the units of rate of reaction are always moles per decimeter cubed per second. Concentration of A is mole per decimeter cubed per, and the concentration of B is mole per decimeter cubed. One of those is going to cancel out. So that the rate is seconds to the -1 divided by mole per decimeter cubed. Bring everything up onto the top line, S to the -1, mole to the -1, dm cubed. That is our, they are going to be our units. Okay, let's work out the numbers then. So K, the rate they tell us is 3.1 times 10 to the -3. The concentration of C is 0.48. The concentration of D is 0.23. Put all those numbers in your calculator. I think you'll get, right, 0.0281. And there's our units. Significant figures, actually, we should give it 2 significant figures because everything's given to 2 sig figs here. I don't think there's any marks going for it if you look in the mark scheme, but so we should get rid of that 1 at the end. 0.028 is the rate constant. I think we need that in the next part of the question as well. So I'll write this down here. Right, okay, so I'll make a bit of room here. Now this is about our Arrhenius equation here. Now the value of K we worked out, we're going to need that, is equal to 0.028. Right, use this equation. Your answer is 3.1, so that's our answer. That's the answer 3.1. For to work out the activation energy of this reaction at 25 degrees C. Right, now here ln A is equal to 6, so that ln A is equal to 16.9. Now when I've marked people doing this, quite often people misread this and they think that A is equal to 16.9. It's not. They worked out the natural log of it already. It's ln A is equal to 16.9. I think if you made that mistake, you end up getting 3 out of 4 marks. Not the end of the world, but that's just read the question. Okay, so we have got to work out EA, so we need to rearrange this equation. So we're going to get, first of all, I'm going to do ln K minus ln A is equal to minus EA over RT. So then multiply both sides of the equation by RT minus EA is equal to RT ln K minus ln A. Get rid of that minus sign, put it on the other side. Okay, so we want minus 8.31 is the units of R. Now it's important to notice here the units of R are in joules per Kelvin per mole. So we're going to get our activation energy here in joules, and we're going to have to convert it into kilojoules at the end. Okay, so we get that. Ln K, well, K is equal to that, so we do natural log of that in a calculator of 0.028 is equal to, 1 minute, okay, is minus 3.57. Okay, so now we've got to put our numbers into this. So EA is equal to, sorry, I did it in the wrong place. Right, so EA is, lung K is, so it's 3.57 minus 3.57, sorry, that's important, minus 16.9 multiplied by the temperature, okay, which is 298 Kelvin, it's 25 degrees C. Okay, if you work that lot out, you get 50,691 joules per mole, and let's convert that into kilojoules. And the least accurate bit of data is this, which is in 2 sig figs, so we should call that 51 kilojoules per mole. So that question was really just all about putting numbers into your calculator and into formulae. Okay, right, some organic now then. So we've got an aldehyde, and that has got 1, 2, 3, 4, 5 carbons, so it's propanal, and it reacts with KCN, and then you add acid, okay, to form a mixture, okay, of a racemic mixture of 2 stereoisomers of that. Okay, so let's name this stuff. So it's always be on the safe side to draw it out rather than do it in your head. It only takes a second. 1, 2, 3, 4, 5. That's an aldehyde. Okay. What's going to happen here is the cyanide is going to attack there, and then that's going to, right, so you're going to form cyanide there, the nitrile, and you have an OH there. Now naming it, you've got to have this as carbon number 1. So that's 1, 2, 3, 1, 2, 3, 4, 5, 6. So that you would call that 2 hydroxy pentane, sorry, hexane now because it's 6, sorry. Hexane nitrile. How would you distinguish between separate samples of the 2 isomers of that? Well, how do you're going to get this? Well, this carbon here is chiral, number 2. It's got 4 separate groups attached to it. It's got that one, that, and that. So it's chiral. How do you distinguish between 2 optical isomers? They will change. They will rotate the plane of polarization of polarized light in opposite directions. One will do it clockwise, one will do it anti-clockwise. Okay, explain why the reaction produces a racemic mixture. Now we need to talk a little bit about the mechanism there. Okay, so we need to say this is the aldehyde, and this carbon is planar. You've got 3 groups around it in no lone pairs, so it's trigonal planar, and you've got bond angles of 120 all the way around it. Okay, now the nucleophile, this is flat, will attack from above or below. Okay, so the cyanide, which is the nucleophile, is going to attack either from above or below. If it attacks from above, sorry, below, you're going to get 1 optical isomer. And if it attacks from above, you're going to get the other optical isomer. So, and the chances of it doing either attacking from above or below are exactly the same. So you're going to get a 50-50 mixture of the two isomers. Okay, so for 3 marks, that's all you have to say. It's a pretty standard sort of question, that actually. They ask that quite a lot. Right, an isomer of this stuff, of propanal, reacts with potassium cyanide followed by dilute acid to form a compound that does not show stereoisomerism. Draw the structure of the compound formed and suggest why it doesn't show it. Okay, so we're going to get, you know, the isomer is going to have a carbonyl group in it, okay, and it's going to have 5 carbons, right? And we know that after you have an attack by a nitrile, you can have a nitrile stuck onto onto the carbon. You're going to have the OH, this carbonyl thing turns into an OH, and then you're going to have, it's a ketone, you're going to have 2 R groups. Okay, you can have those 4 things stuck to the carbon. Now we don't want this carbon to be symmetric, so that means these 2 R groups have got to be the same. Right, we've got 5 carbons to play with. Okay, so that means if we have an ethyl group, if that's C2H5 there, and if that's C2H5, that's going to be, yeah, that's going to be 5 carbons altogether in that, not excluding the cyanide, of course, and that's going to give us the right structure. So the compound formed will be right. We've got the cyanide, the nitrile, the OH group there, and then we want CH2, CH3, and CH2, CH3. Okay, that's the structure you need to draw, and just to remind ourselves, that will have actually come from this ketone, which is an isomer of propanal. They're both C5H10O. Okay, so here is a question now about polymers. Well, not quite polymers, it's just esters though. Ethanoic and ethane 1,2-diol react to form the diester. Okay, so if you draw a structure of the diester, now what's going to happen there is you're going to have C8, this is the ethane diol, and on each end you've got 2 molecules of ethanoic acid. Each end is going to react with an ethanoic acid molecule, so CH3OH on that side, and here, okay, what's going to happen? You're going to lose water here and here. You're going to form 2 ester linkages. I'll just rub that out. So you're going to get a bit of a long bond there, but that's what you're going to get, and you're going to get the same on the other side as well. So that's the diester, C6H10O4. If you check the number of hydrogens, that's right there. Okay, now I think it's going to go into equilibrium now, yeah. So a small amount of catalyst is added to a mixture of the ethanoic acid and the ethane diol, and it's left to reach equilibrium, and we've got to find out the moles at equilibrium. Now, just to remind ourselves, I've just pasted in the equation again there. So they've got at the start, I like start moles and equilibrium moles. I'm going to put in there, I'm going to squeeze in there used up moles. Okay, so how are we going to go about that? Well, at the start we have, so 0.47 of that and 0.18 left over. So how much have we used up? Do a subtraction, 0.47 minus 0.18, that's equal to 0.29. Okay, so we've used 0.29 of that. Now, if you've used 0.29 of ethanoic acid, we will have used 0.29 of that. We use half of that, so that's half times 0.29. Because every time we use 2 moles of ethanol, we only use 1 mole of the diol. So divided by 2 gives us 0.145. So let's work out how much of the ethane diol have we got left over. So it's 0.205 minus 0.145. That gives us 0.06 of that left over at equilibrium. Now, how much of these are we going to form? So let's have a look at the ester. Well, when we use up 1 mole of the diol, we make 1 mole of ester. So that's going to be 0.145 of ester there. And we form double the amount of water, so that's going to be double that, which is 0.29 of water. That would be the answer to that. Okay. Write an expression for the equilibrium constant Kc. Okay, and then the total volume doesn't need to be measured in order to correct Kc to be calculated. You've got to explain why. So I've just posted that in again. So I'm going to write down, right, so what we've got Kc is C2H10O4 to the power of 1 multiplied by H2O to the power of 2 divided by I just write that diol because it's quicker to the power of 1 and acid to the power of 2. Right, now why don't we need to know the volume? Well, it's because if you just write down, you've got the same number of moles on both sides of the equation, so you'll get them marked, but I'll just explain why. So you've got 3 moles on this side and you've got 3 moles on that side. So Kc is also going to be equal to, instead of the concentration of that, I'm going to put the moles out, so I'll do it in red. So that's going to be C6H10O4 over V, where V is the volume, multiplied by H2O over V all squared. Let's simplify that out straight away. That's going to be moles of H2O squared over V squared, and we're going to divide that by the concentration of diol here. That's going to be diol over moles of diol over V, and acid, well, that's going to be acid like the water. It's going to be acid squared over V squared. Now you can see there that all of those V terms are going to cancel out. So that means all we need to know is the number of moles, which I've done in red, rather than the concentrations, which I've done in blue. You can just put the number of moles in there. It doesn't matter what the volume is. Doesn't affect the value of Kc. So you can do that whenever you've got the same number of moles on both sides of the equation. Okay. Right. I'm just going to copy this expression for Kc. So I'm going to need that in the next bit. Okay, so we've got our expression for Kc there. Right, and it says different mixture at the equilibrium. You've got all of these numbers of moles here, yeah, and we've got to calculate the concentration of the moles of ethane dioic acid, and they give us the value of Kc. So let's substitute into that expression for Kc then. Right, and let's call the volume V again. So Kc, which is equal to 6.45. Actually, what I will do is I will rearrange this first of all to get the concentration of acid. Okay, so let's do that. So acid concentration squared is going to be equal to the diester concentration times by water concentration squared divided by the diol concentration multiplied by Kc. Right, so now we're going to start putting in some numbers. So acid concentration squared. So I'm going to call that moles acid over V, all squared. And so, of course, what that lets us do is we can multiply that bracket out, and we're going to get moles acid squared over V squared. And that is equal to the moles of the diester, 0.802 over V, so concentration, multiplied by the moles of water. So the concentration of water is 1.15 over V. I'm going to square that, and that's squared there. Divided by the concentration of the diol, which is 0.264 over V, multiplied by the value of Kc. Right. So I'm going to divide both sides of the equation by 1 over V squared. So I'm going to cancel that out. There you go. And then I can cancel that V with that V. And now all we've got to do is, well, substitute that value of Kc is actually, what is it? They say it is 6.45. So put all those numbers into my calculator, and I'm going to get moles of acid squared. That gives us 0.622. Take the square root of that to get the moles of acid. And that on a calculator gives 0.789 moles of ethanoic acid. Okay, so all those V's will go. Right, okay, now on to a bit of biochemistry. Okay, so use the data book to help you answer this question. So I have pasted in the relevant bit of the data book there, just the structure of the amino acids. I'm going to get rid of this. Okay, so, right, draw the structure. There's Viteran formed by phenylalanine. So here's phenylalanine. So I'm going to draw, right, so we've got, there's the carboxylic acid group. There's the amine group. The R group is CH2, benzene ring. Now we want this Viteran form, so we've got to deprotonate the carboxylic acid, so that becomes O-, and stick a proton onto there to charge the, okay, so that's this Viteran form of phenylalanine. That's pretty straightforward. Now let's draw the structure of serine at high pH. Now this is a bit of a trick question, so I'm going to just modify this. So I'm going to rub out that there. I'm going to put my serine in there, so all I've got to do is turn that into a, look here, CH2OH. I'm actually going to draw it out in full. Right, let's get rid of, let's just make sure that normal carboxylic acid and make that a normal amine. Get rid of that. Okay, so now it says high pH, so that means it's very alkaline, so we're going to remove a proton from there. Now, will alkali remove a proton from an OH group, from an alcohol group? No, it won't touch it. It's a really common mistake. People think somehow because it's on an amino acid it's different or something, and they say, oh, that's going to become O- as well, which is not. It's not going to become O-, that will stay as OH, just like any normal alcohol group would do. So that's the and they're definitely trying to confuse you there by asking about serine because it's got that OH group on it. Okay. Draw the structures of both dipeptides. Right, so I'm going to get this data sheet a bit further down. When phenylamine phenylalanine, sorry, reacts with serine. Okay, and these structures show all the atoms and bonds in the amide link. So let's just draw any old two amino acids. So I'm going to have this one here. So here's the amino group. That's always H. That's the R group. And we've got the carboxylic acid group there. And I'm going to draw them head to tail because it's going to form a dipeptide with this one. And they draw them out like this, look in the data book. So if you remember that, makes it easy that they're drawn out sort of head to tail. And now to form the amide or the peptide link, all we're going to do is we're going to lose the water here. Okay, so let's get rid of that. And now we're going to form a, so we've got rid of the water, and we're going to form a new bond between the carbon and the nitrogen. There's nothing to make it, but it just looks a bit neater if you do it like that. That oxygen looks particularly scruffy. Change that. So we've got that. That's any dipeptide. Now it says between phenylamine and serine. So let's say this one was phenylamine. So all I've got to do is now put the R group for phenylalanine on there, and the R group for serine is that. That's one of the dipeptides, and all we've got to do to draw the other dipeptide then is just swap those. So copy the picture out again and swap the two R groups around. So in this case, the phenylalanine is, we say it's the N-terminal one in the dipeptide, and the serine is the C-terminal one. All we've got to do is swap them. So let's just change that to CH2OH and change that to CH2, so it's in a different color, the benzene ring, and that's the other dipeptide. So you've got your two drawings for the price of one. Okay, you just swap the R groups around. Okay, 6.4. Right, so this is a recall question. Okay, of a mechanism. An amide link is formed when acyl chlorides react with a primary amine. Name and outline a mechanism for the reaction. Okay, and give the UPAC name for the product and the name of the mechanism. Well, the name of the mechanism is nucleophilic addition elimination. Right, so let's start off with the acyl chloride, CH3, CH2, Cl, and the amine, it's easiest if you draw the amine backwards. Well, you've got a delta positive on that carbon. You don't need to draw that. They never insist on that. AQA. And you've got a lone pair on this nitrogen. You do need to draw that. So the first curly arrow, that is going to attack that carbon. That means one of the bonds of this carbon's forming is going to break. It's the pi bond that breaks. The electrons go into the oxygen. So we're going to form this intermediate now. Oops. The intermediate we're going to draw is, so we've got CH3, CH2. The oxygen has now become O minus. I'll draw a circle around that. We've still got the, sorry, that's not right at all. Missing a carbon, CH3, CH2. The oxygen has now got a minus charge on it. I'll draw a lone pair in there. It's got three lone pairs. I'll just draw one because we need that for later on. The chlorine there, and the nitrogen is still forming bonds to two hydrogens. Okay, that nitrogen is positively charged. It's usually a bit of a giveaway. Whenever nitrogen is forming four bonds, it's positively charged. Right, so the next step in the mechanism is the pi bond reforms. So that pair of electrons comes down and reforms the pi bond. Of course, this carbon is now forming too many bonds. So it breaks the pair of electrons and there goes the chlorine to form chloride. So if we draw this intermediate, CH3, CH2, C, double bond. Okay, the chloride's gone. We've still got two of those on there. Let's put the plus Cl minus in here. And the final step is, well, is one of those hydrogens, like the pair of electrons, goes back into the nitrogen to form the final product. You can combine those two last steps into one step. Lots of people do. I prefer to do it as two separate ones. So we get that. Okay, now what is this called? It's an N-substituted amide, and they're kind of named in a rather confusing way, I always think, because you pretend this bit, right? This is like propanamide, propanamide, but it's stuck onto it. It's got an ethyl group, so we call it N, because it's stuck onto the nitrogen. N-ethyl propanamide is the name. Okay, now, right, the last question before we stop this video, because it's getting quite long. Now, test tube reactions can be used to identify functional groups. You provided with samples of each of the 4 compounds. Describe how you could distinguish all 4 compounds using the minimum number of tests. Okay, and you describe what is observed in each test. Now, there's a few different ways of doing this. I won't do all of them because it's quite long, but I'll do a few of them. Right, what you can do first of all is, if you look here, you've got 2 of them have got carboxylic acid groups. Okay, so you can identify them from the other 2. So if you add solid sodium carbonate, you will get effervescence, fizzing. You'll get that with K and M. So you can tell which 2 are, you can't say which one is which, but you can separate. You know K and M, and you know that the other 2, by process of elimination, must be L and N. So we've done 1 test, okay? Nothing will happen with L and N, no visible change. Now, how can we distinguish between K and M? Well, I think the easiest way to do that is the fact that this has got an alcohol group, and it's a secondary alcohol group. You can oxidize that with potassium dichromate. So then you would add potassium dichromate, and it's got to be acidified, plus acid, and you warm it. Now, in the case of K, that can be oxidized because it's a secondary alcohol, yeah? So that will go from orange, potassium dichromate color, to green. If you like, the alcohol is reducing the potassium dichromate to green. Whereas M, you can't oxidize anything in that molecule with potassium dichromate. So M, no visible change. NVC, no visible change. Okay, so you've done 2 tests now, and you've identified, but now we've got to distinguish between L and N. A good way of doing that, I think the only way really, is if you look, that's got an aldehyde group, which of course will give a positive reaction with Fehling's test, or with Tollens test, let's say Fehling's. So do Fehling's on both of them. So our 3rd test, Fehling's. N will give you a positive test. You'll get a brick red precipitate with N, and there'll be no visible change with M. It will stay, if you like. So this is going to be blue solution to brick red precipitate. Probably best to say that on the safe side, rather than just brick red precipitate. M, it will just blue solution remains. Okay, so you can do it that way using 3 tests. There's another way you can do it with 3 tests, so I'll just do that. There are other ways. That, to me, seems the most obvious way of doing it. Do another one. Right. Now, the other way you could do it is both L and N contain this bromine group, and you can hydrolyze that bromine off if you add water. Okay, you get the water will. So add water to both of them. So the first test is add H2O and silver nitrate solution. Well, so you just add silver nitrate solution, not acidified. Best not to acidify it. And what you'll get is you get bromide ions will be released, and they will form a cream precipitate with the silver of AgBr. So you can distinguish L and N, and because they'll give you the cream precipitate, and K and M won't. Okay, and then you can do exactly what we did last time. You can distinguish between K and M by doing the potassium dichromate, because it will oxidize that. Okay, so that you could do that, and then distinguish L and N the same way by using the failings test. So that would be a total of three different tests as well, which is minimum. Right. Okay, and as I say, there are other ways of doing it, but just two possible ways there. Okay, so leave that there, and the second half will be in the next video.